We're now going to take a closer look at that definition for the directional derivative that we established previously, and then see again if we can refine our process just a little bit, or maybe a lot. Let's start by revisiting what we define as our directional derivative. So with this, we need a surface, and I'll start out with a function of two variables. It's always a good place to start. And then we needed a unit vector, and that unit vector, let's say, would have components u1i and then u2j, right? So this one is a unit vector as per definition. And then we needed a point, right? So we needed the point x0, y0, and we're going to assume that our surface is nice and continuous there and differentiable there. So here we can just say a point that's in the domain of this surface. Now remember what we did. We used the point and the unit vector to come up with a parametric a set of parametric equations for the line that passes through that point and then moves in whatever direction we define, right? So we used both these two things, and we came up with an equation for x, which would be the x value plus some parameter times u1. And again, I used s for that, no particular reason. And then we also came up with the corresponding equation for y. So we had that y is equal to our y0, right, plus u2 times s. And then what we ended up doing is we essentially plugged in, it's like we evaluated the surface along this line, which is defined parametrically. And then we took the derivative of the resulting curve, and then we evaluated at s equals 0 to get the particular directional derivative. But if we think closely, this setup, so look at this. This is saying that z is a function of x and y, and then these two equations now, x is a function of s, right? Because the point is fixed and the u1 component of my direction is fixed. So x really only depends on s. Similarly, y only depends on s. So that sounds a lot like what we were doing with the chain rule. So let's actually represent this scenario using a tree diagram that we previously did, right? So we have our surface z, right? And z, or if you want to use f, you could do that, that's fine. But z depends on x and y, right? That these are independent variables, right? But then when we now throw the line in the mix with these parametric equations, the x value on the line depends on s, and so does the y value on the line. It depends on s. So our tree continues to grow. It looks like this, right? And essentially, you notice what we ended up doing. We ended up taking the derivative of the surface with respect to s. So we kind of eliminated the middle, but now we're not going to eliminate the x and y. We want to see, like, what is the real significance of the x and y here. Now let's go ahead and decorate our tree, even though it's not, the festive season. It's a festive season in some parallel universe somewhere, right? It's Christmas somewhere, just like how people say, oh, it's 5 o'clock somewhere. Well, it's probably Christmas somewhere. Let's go ahead and decorate our tree with our partial derivative. So this one will be the partial derivative of z with respect to x. So we've seen that. And then this will be our partial derivative of z with respect to y. And then we know, we can use the partial derivative notation here. That's nothing wrong. This is the partial derivative of x with respect to s. And then this is the partial derivative of y with respect to s, right? Now, these, because we're doing something very general, I don't know what f is, so I can't write these down specifically. But what I could say is, I could say that this is my, I could use my alternative notation and say that this is f sub x. And now, since we're at this specific point, I could say, because that's the goal, right? We're trying to find the instantaneous rate of change of this surface at this point in this direction. So I could say, well, I could figure out what that partial derivative is at that point. And then I could do the same thing. Oh, sorry, I have this should be y, not x. Right, so here I would differentiate with respect to y, evaluate it, and then for this one, I'll differentiate with respect to x and evaluate it. So my x0, y0, so we have that. Right, so we have a little bit more information about, what rate of change would go along this branch and then this branch. Now, when we think about the rate of change of the line, because that's what we have to do, for these two remaining branches, well, the rate of change of the line, that's just the direction vector. Because if I look at this equation and differentiate it with respect to s, which is what this symbol is telling me, well, this is a linear function. So when I differentiate with respect to s, the constant x0 goes away, and then I'm going to be left with the constant that's multiplying my parameter s. So this is just u1. Right, so that works out nicely. And then similarly, when I differentiate this y equation with respect to s, the y0 goes away, and I'm left with the constant that's multiplying my s term right here. So I have u2. So now, if I want to find the instantaneous rate of change, so I want to differentiate my surface, and find the instantaneous rate of change at this point in this direction, which is my directional derivative, the chain rule gives me a nice way to do that. So this implies that if I want the instantaneous rate of change, so the instantaneous rate of change, which is our derivative, right, of my surface, so of f, at the point x0, y0 in the direction of u. It's always a mouthful when you say this, but there are a lot of things that go in it. Well, that's just our big D subscript u f evaluated at x0, y0. That's just our directional derivative. But now by the chain rule, I could look at my tree and write down what I'm supposed to do. So it's all the ways that s will affect the rate of change of z. So one path, right, is along these two branches, right? So through the x intermediate variable. So I would take this rate of change, which I'm going to write down as fx of x0, y0, and then multiply it by u1. That's what the chain rule says. I take this rate of change and multiply it by that rate of change. But then there's an alternative way that s can affect z, and that's through the y variable. So then I have to add that alternative path, which now, again, I take the product of this rate of change and this rate of change, and I end up with this alternative formula for computing the directional derivative of my function at this point in this direction. And look at what it says to do. It simply says, take the partial derivative of my surface with respect to x, evaluate it at the point, multiply it by the x component of the direction vector, and then add to that the partial derivative of y evaluated at the point multiplied by the y component of the direction vector. And this is our alternative thing, right? So let's just kind of summarize. Right, so this is our alternative formula for finding the directional derivative of a surface at a particular point. And now you notice that we can express it in terms of partial derivatives, right? So that's good, right? But it's not just one, it's essentially all the first partial derivatives, and it's like they're being weighted by these constants. It's almost like a weighted average of the individual rates of change. So this is the rate of change with respect to x, this is the rate of change with respect to y, and then by multiplying it by u1 and u2 respectively and adding them, you're essentially finding a weighted average of these partial derivatives, right? So similarly, there's a nice one if your surface is of if your function is of 3 independent variables. So I'll just say similarly, right? And these are actual theorems, and we essentially just gave the proof of the theorem above, but I'm going to be a little bit informal today, so I'll just say similarly for let's say w equals f of x, y, z, right? At x0, y0, z0 in the direction, so in the direction u equals u1i plus u2j plus u3k, again, unit vector, that's important, that comes from our initial definition. So in the direction here, let's write down what it looks like for a function of 3 independent variables. So we could say that the directional derivative in the direction of u of my function at the point x0, y0, z0, that's equal to, so we would take the partial derivative of w or f, evaluate it at x0, y0, z0, multiply that by u1, and then repeat that process for the remaining 2 independent variables. Next, take the partial derivative with respect to y, evaluate it at x0, y0, z0, multiply it by the y component of the direction vector, and then finally take the partial derivative with respect to z, evaluate it at the same point, x0, y0, z0, and then multiply by the z component of the direction vector, right? So now we have a way, no matter how many independent variables, right, our function has, we have a way of computing the rate of change of that function in any direction. And again, both of these that I've highlighted in red, I will just say, here is the disclaimer that we have to make, right, for liability, because we don't want to come back and get sued for not making this disclaimer, but provided all partial derivatives exist, right? So provided all partial derivatives, right, exist. And there we go. So that is one way to an updated version of how we can compute directional derivatives, right? So let's take a look at an example illustrating this, and I'll do an example of a function of 3 variables. So let's say, and we'll do an example where it pretty much has all the key steps, right? So let's take a look at this example. And so here's our function of 3 variables. It is x squared y minus yz cubed plus z. And let's say here's our point. So our point is 1, -2, 0. And then let's say our direction is let's say a, and there's a reason why I'm using a and not u. So 2I plus j minus 2k, right? So here's the setup, and what are we going to find? We're going to find the directional derivative in this direction of this function at this point, right? So again, we can think of it as the instantaneous rate of change at this point on this surface if we were to move in this direction, right? Now, so let's think about everything that we're going to need. Well, the partial derivatives are going to play a big role, so maybe we could start with that, right? Let's go ahead and start with our partial derivatives, and I'll just use the f sub x notation. So, and I'll go through and find all three. So f sub x of x, y, z. So this is where we're going to differentiate with respect to x, and we're going to treat y and z as constant. So the first term will give us 2xy. There is no x in the second and third term, so those are 0. I'll just write them down for emphasis, but those go away. So we have it like that. Now let's take our partial derivative with respect to y. What do we end up with? Well, we'll have just an x squared because we're treating all of this as a constant, and when we differentiate y with respect to y, we get 1. So this constant multiple comes down. Similarly, the minus z cubed will come down because, again, all we have as far as y is concerned is y raised to the first power. So it's a linear term, and you can say that the z cubed is its coefficient, so minus z cubed. And then I don't have a y in this term, right? And then finally, our partial derivative with respect to z. There is no z in the first term, so we have 0. And then now we can use our power rule, but we have our constant multiple of negative y, so it's going to be negative 3y z squared. And then when I differentiate this third term, so z with respect to z is just going to give us 1. Here we go, right? So there we go, we have our partial derivatives, but then we're going to need the partial derivatives to be evaluated at this point, right? So I'll just do that right next to this one. So I'll take my f sub x evaluated at 1, negative 2, 0. So when I plug stuff in, I don't have to worry about the 0 because this doesn't have a z. So it's really just 2 times 1 times negative 2, so that's negative 4. Let's take the partial with respect to y and evaluate it at 1, negative 2, 0. In this one, we have to take the x value and square it minus the z value, square it. But the z value is 0, so all we have is 1 squared, which is 1. So that's good. And then finally, let's take our partial derivative with respect to z and evaluate it now at our specific point, 1, negative 2, 0. And notice what happens here, because z is 0, this term all goes away, and I'm just left with so it's basically 0 plus 1, so that's 1, right? So essentially, and again, the way you can interpret these separately, this is the slope of the surface, or the function. Yeah, it is a surface. It's just a surface in a higher dimension, so maybe a hypersurface. So this is the slope of this hypersurface in the x direction at this point. So if I start at this point and I move in a direction that's parallel to the x-axis, then my function value will decrease at a rate of 4 units of f per unit of x, y, well, actually just x, since y and z aren't changing. And then you can interpret the other two partial derivatives that way. This would be the slope specifically in the y direction. This would be the slope specifically in the z direction. But now look at our change. We are moving from 1, negative 2, 0. We're moving in a direction that will be parallel to this vector. So all three of my independent variables are going to be changing if I start from this point and move in a direction that's parallel to this. The other thing that you have to be careful in this process is if the vector that's given is not a unit vector, right, we have to normalize it because our definition requires that the direction vector be a unit vector. So notice, that's why it's specifically used as u, and then any other kind of generic label can be used. Even if the letter u is being used, don't always assume that this is a unit vector, right? And I think it's pretty clear that this one isn't, but how could we know for sure? Well, we can find the magnitude of this vector. So I'm going to ask this question. So is that vector a unit vector? Well, how do I check? I compute its magnitude. So I'll have to do the 2 squared plus the 1 squared plus the negative 2 squared and take the square root. And I end up with 4 plus 4, so that's 8 plus 1. So this is a nice question set up. We get the square root of 9. So this magnitude is 3. So since this is not 1, right, a is not a unit vector. So what do? Well, we have a way of finding the unit vector that acts in the same direction as a. So we have to normalize a. So normalizing a is going to give us the u that we need, and the components of that vector those are the components that we will use with our alternative formula to find our directional derivative. So normalizing a, that's going to give us our unit vector, and that's 1 over the magnitude of a times a. So remember the magnitude of a is 3, so we're going to end up with our unit vector be 2/3 I plus 1/3 j minus 2/3 k. So now, again, going back to, I'm not going to go back to the formula, but this, I will just highlight it here. This is our u1. This is our u2. This is our u3, right? So always make sure that the components that you're using as your u1, u2, and if in this case u3, make sure that those components are the components of a unit vector, right? Actually, I just saw something here. I forgot the word unit. So this is not, of course it is a vector, but it's just not a unit vector. Okay, so here's our last step. So our directional derivative in the direction of u of this function at the point 1, negative 2, 0. So the formula says it's, again, I'll write it down as f sub x evaluated at 1, negative 2, 0 times u1 plus the partial with respect to y evaluated at 1, negative 2, 0 times u2 plus the partial with respect to z evaluated at 1, negative 2, 0 times u3. And we're going to come up with a number. It's a number because it's a rate of change. It's a scalar. And what this is, so we got our negative 4, and then that will multiply our 2/3. And then we have our positive 1, that will multiply the 1/3. And then we have another positive 1 that will multiply the 2/3, or I should say negative 2/3. So what do we end up with here? We have negative 8/3 plus 1/3 minus 2/3, so that's negative 9/3 for a directional derivative of negative 3. And what does this mean? It means that our surface is decrease. So again, at this point in this direction, our function or surface or hypersurface is decreasing at a rate of 3 units of f per unit of x, unit of y, unit of z. So it looks like this. It would be units of f and then per unit of x, unit of y, and then unit of z, right? And there you go. So that's what it looks like. And this, I would say, represents a fairly standard, typical type of question where you might have this additional, this extra step of normalizing because the direction that's given is not a unit vector. All right. Okay. So so when the title of this video is directional derivative and gradients. What do we mean by gradient? Well, let's look carefully at this formula again. So let me draw a line here. So let's say, so we have now a very, what I think is a effective and efficient way of computing these things. It involves partial derivatives, which we are becoming masters of, if not already mastered, right? Maybe there are different levels of mastery. There you go. But yeah, so we have this way of computing it, and let's say this is what, I'll just do it for a function of 2 variables. Now, if you look closely at what's going on here, look at what it is. We have a partial with respect to x multiplying the x component of the direction vector, and then we have a partial with respect to y multiplying the y component of the direction vector, and these two things are being added together. Think about that. These, it's like something with respect to x multiplying something in the x plus something with respect to y multiplying something in the y. That almost smells like a dot product. It almost looks like I can express this as a dot product. Like if I were to do something really crazy now and write down a vector where the first component of this vector is in fact the partial derivative with respect to x evaluated at that point, and then again just do something really wild. Just take this partial with respect to y and just make that the second component. And then, since we're just doing all this crazy stuff, what if we made another vector? Because we just love vectors, where I would use now the I would literally write down the unit vector as a true vector, not just the components, but actually put it in those angled brackets and say then u1 goes there, u2 goes there. And again, if I use my dot product on these two vectors, right? So if I find the dot product of this vector with this vector, I'll get exactly the same expression there. So this now gives us a way, again, it's the same set of operations, but it gives us another way of denoting, right, of denoting a directional derivative. And the reason why this alternative notation is really important is that it allows us now to formally say something about a vector that looks like this. Essentially, this, I'll just say it in quotes, this is a vector of all the possible first partial derivatives of my surface. So this is a vector of first derivatives. And it turns out that vector is really important. So not only does it give us a nice way of denoting our directional derivative, it's going to serve a lot of purposes going forward. And this vector is what we define as the gradient of the surface, right? So even if I don't plug in points, so even if I just have f of x, y, then I can write down a gradient vector which will also depend on x and y in general, right? So that leads us to this definition, right? So the gradient stuff isn't something like completely radically different. It's just now looking at this expression a little bit more and saying, hey, let's give this thing a name. Let's give this thing a name. And this is the name that it's given. So if z equals f of x, y, right? Where f is differentiable, right? And again, let's just state that differentiable is just saying that we have continuous first partial derivatives. So these first partial derivatives are nice and continuous. So where our surface is differentiable, the gradient, right? So gradient, the gradient of f. And again, let's do the notation and the definition all in one. So is denoted and defined as, and this is what it is. So there are a couple notations for the gradient. Sometimes we will abbreviate the word gradient to just grad. So you might see something like this, grad of, sometimes you might put the name of the function or the name of the independent variable in parentheses. So it might look like this, or like this. But the other notation is, it looks like upside down delta. So it's a triangle, you know, it's a little triangle shape. This stands for the gradient. And again, a lot of times we would indicate that we're taking the gradient of this function. And what's interesting is when you take the gradient, you do get a function that also, well, actually you're going to get a vector that depends on the same two variables as your original function, right? So this is kind of this is the most common way to denote a gradient, and the way it's defined is this. All you do is you form a vector, and the first component of that vector is the partial derivative of your surface with respect to x. And then second component is the partial derivative of that surface with respect to y. And there you go, right? So the gradient is this new, it's a new operator. It's called an operator. And what it does is when you apply it to a function of several variables, it returns a vector that makes up where the components are the respective first partial derivatives, all the possible partial derivatives of that surface, right? What does it look like in 3 variables? Right, so I'll just say similarly, if w is a function of x, y, z, then again, I'll go ahead and just use this symbol. So the gradient of f, and we could put w there if we want. I'll just go ahead and use the f. So like this. Again, this is going to produce a vector where the first partial derivative goes in the first component. First partial derivative with respect to x goes in the first component. Then the first partial with respect to y goes in the second component. And then the partial with respect to z completes it with the third component, right? And there you go. So that's the gradient. Here's just a quick example of a gradient calculation, and then this will wrap it up for us, right? So our example, so let's say w, oh, that doesn't look like a w. Let's say w is equal to e to the xy times, let's say, the cosine of z. So let's say that's our surface, right? And we want to write down what the gradient is. So the gradient of W, again, this will depend on those same three independent variables, but the difference now is we're creating a vector, and what that vector is comprised of is essentially all the possible partial derivatives in the order x, y, z, right? So let's see if we can just write it down. So let's look at this, and if we're going to differentiate this with respect to x, that means we're treating y and z as constants. But when I differentiate the exponential, because of the chain rule, that constant y has to come down. So it's going to be y e to the xy, and then the cosine of z, that's a constant multiple, that comes down as well. When we differentiate with respect to y, something very similar. The x is now treated as a constant, as is the z. So the constant multiple here is x. X is your constant, and by the chain rule, that constant has to come down and multiply the e. The e is never going to change, right? And then we also have the cosine of z. And then finally, partial with respect to z, then now x and y is being treated as a constant. So the entire e is a constant multiple of this. But then when I differentiate cosine of z with respect to z, I'll get negative sine of z. So I'll put that negative in front, and we'll have e to the xy, and then sine of z like that, and there we go, right? So that's the gradient of this surface, right? And what we saw earlier is that the gradient is an alternative way of setting up and computing this directional derivative. But not only that, the idea that we can use a dot product, it's going to allow us to look more closely at this gradient thing and see what kind of interesting properties this gradient has, right? So if you want to see more about the gradient, again, just hop on over to the next video, and I'll see you then. Bye for now.